Good morning.
Good morning. Good morning. We're having phenomenal turnout for the last discussion. I'm so
I can't
happy.
hear anything. Why can't I hear anything? Oh, that's why.
Did you have us muted?
Oh, there we go. That's why I was outputting to the wrong device. Okay, there we go. Hello. How are you doing? Good morning.
Filtering in shortly. Okay, so I'll just start filling out the agenda, although we're not start just yet. A bit about
I got a quick question. So if you have an op amp and then two resistors going out of the output that go to ground, the output resistance, would it just be R1 plus R2 in parallel with R out um of the op amp?
Okay, so you said both of the resistors were in parallel.
No, they're in series. So you have two resistors in series that go to ground from the output, and then you have the op amp, and you're trying to figure out what's the output resistance. And
If you're
so
finding
I
if you're finding the output resistance of the circuit, then it's what you said, I think. Although
perfect. Okay.
yeah, yeah. I mean, the output resistance on the amplifier is given, right? So that's
Yeah, it
probably what
is.
you're
I
asking.
just want to make sure that like we're not supposed to like do something funny with like GM or something like that.
If you're asking about a specific question on the homework, let's see about that one. So,
It's just one A. I just want to make sure because like that's pretty fundamental to the rest of the problem.
what is the output resistance of the circuit? Um, I think uh, I think you have the right idea. Although I'm not certain if you. Yeah. So when you put it in feedback, the output resistance will change, and so that's something that the problem is intended to help you evaluate. But the first part is kind of just like an open loop output resistance, and yeah, later on you'll see how that changes. So I think you have the right idea, at least as far as that's concerned, and then maybe what I'll talk about today will elaborate more on the other parts, which will help you with that. Okay, so we might as well just get started. There's a lot of stuff to cover. So on the agenda today are non-ideal op amps, of which the first concept is kind of feedback, and then with feedback we also have closed loop gain, which goes hand in hand with that, and then the concept of loop gain, which I admittedly did not understand until I was in 140, and then probably didn't understand it that well in 140 either. And then also input and output resistance for the amplifier and for the circuit.
So that's closed loop game you said?
Yes, closed loop. And finally, well, there are a few other concepts. So then there's also going to be this concept called GBW, gain bandwidth product. And we also have, other than GBW, we have voltage and current offsets. And then the last thing is going to be slew rate and step response. So did we get around to slew rate in the last lecture, if anyone went?
Yes, you got to run through, right? It's like it causes
Last
your
lecture.
curve to like go flat in the early part.
Something like that. We'll get to it. So, right, to begin with, let's just take a look at feedback. So in terms of general models, we'll have a transfer function g of s. And so as I've drawn it right now, we have what is kind of called like an open loop system. But what we can do to change the behavior of the system is to put it in feedback. And so we can add this block here, make this a summer. And now we have a closed loop system with a feedback factor of f. And so the thing to note here is that the gain is the transfer function here is necessarily different. So if we had our input x of s and we had our output y of s, in the open loop configuration, the transfer function y of s over x of s was just g of s, right? But when we put it into closed loop, we can use something called Black's formula or just derive it from scratch like I do every time to see that the transfer function here from the input to the output is a bit different. So just to collect terms, we have x of s. So we have y of s is equal to g of s times x of s minus f times y of s. And if we collect terms on the left side, we have y of s times 1 plus g of s times f is equal to g of s times x of s. And then that results in y of s over x of s is equal to g of s over 1 plus g of s times. So this hopefully was covered somewhat in lecture, but essentially what we see here is that our transfer function has decreased, or it's in a different form now. And so if f is something like 1, then there's a chance that, in this case, we're going to have a probably lower amplitude gain. So in our examples, usually G is some sort of amplifier. And so we'll have some sort of lower gain. But as we'll see later, we might have a greater bandwidth. So this is just what feedback is. And yeah, this is kind of an overview. So yeah, in this case, if we wanted to find the closed loop DC gain, we'll see that occurs when s is equal to 0. So in this case, the DC gain is going to be g of 0 over 1 plus g of 0 times f. So if f is something like 1/2, if f is 1/2 and g of 0 is very, very large, much greater than 1, then what we'll see is that this is approximately going to be equal to 1 over f, which is 2. So, this is kind of an example of the gain, the closed loop gain being much smaller than the open loop gain over here. But we can possibly see that this will help in other ways a little bit later. So any questions about that setup?
Sorry, so why are we looking, so how are we, like, what was the purpose of looking at it at DC? Just like in general, or?
So the purpose of looking at the closed loop DC gain is just to see, it's kind of just an easy point of reference, I'd say. And then also, if we put in a low frequency around 0, then we can see what the gain would be. And if this is a typical single pole system, what I'll kind of derive a little bit later on is just that a closed loop system is also going to be still a single pole system, but the bandwidth will be increased. And so the frequency response will change in some ways, but that's kind of only with respect to the location of the effective location of the pole. Whereas in this analysis is just like a starting point. I'm not sure if that made sense, but hopefully as I go along it'll make more sense. So yeah, closed loop gain, that is that. The next concept is loop gain. So if we redraw that system again, the feedback system, we had the summer over here, and this is a minus sign. We see that there is a feedback path. So what we'll define as the loop gain is the path from x of s back to x of s, possibly or necessarily through the feedback. So in this case, what we're going to do is we're going to, so to find this, we're going to break the feedback loop. Where it returns to x of s, and we're just going to find the gain along that path. So in this case, that means that I'm going to break the feedback over here. So this is broken. This would have been a minus sign over here. Mm-hmm. And so depending on your definition, the loop gain is therefore f times g of s. So we see that x first goes through g of s, and then it arrives here, and then to get back to x of s, we go through a gain of f. And so, in some definitions, we include the minus sign here because, that isn't assumed in the system model. But in this case, we're going to generally just assume that the minus sign is included. So we're just going to call this the loop gain, which is T of S, or T for short. Does that make sense?
So didn't we just turn into open loop then?
That's a good question. So the purpose of this analysis isn't to, so this isn't actually how this model is going to be operating. That's a great point. But what we're using this analysis for is to see how, what x of s is seeing when it's, when the feedback is being applied. So if you can imagine, even if we connect the loop back, this value here is still going to be g times f times x of s, right?
Yeah.
So we're breaking the loop just to make sure that you don't accidentally confuse the input value with what we're trying to find, something like that.
I see. And then what is T of S?
T of S is, T means loop gain. That's like the symbol for loop gain.
I see. So it's just telling us what the gain is of ours. Okay, makes sense. All right.
Yeah, the gain in the loop.
The gain in the loop. Okay.
Yeah. So if we're good on that, we can briefly cover this loop gain concept. So this has ramifications for the frequency response of our system. So frequency response ramifications. And so if we define the value, the DC value of our loop gain to be T, then we'll see that that's equal to f times the DC value of G, which we'll call f times G naught, something like that. So if we assume, and this actually tends to be the case, if we assume that the core amplifier has a transfer function dictated by something like this over omega p. In this case, this is a single pole settling system, and it has some DC gain, which will usually be quite high, and then at some frequency omega p, we see a drop off in the gain. So It'll
Wait,
be
sorry, how do we get
something
to this last line here?
which one?
Why are we saying that G of S is now?
So before our analysis was very general. So we were saying for any G of S, the resultant kind of closed loop gain is going to look like what I did in the last page, right?
Right?
But now we're giving a name to G of S. G of S is, in general, for amplifiers, is going to look something like this.
I see, okay.
So this is what the magnitude transfer function is going to look something like over here, and we're going to have omega p here, and G of O, or G naught is going to be there. So if we want to see how what the closed loop transfer function is going to look like, or kind of evaluate its corresponding frequency response when we put it into feedback, then we can write that out as well, because now, I mean, we found that in the last part, right? So y of s over x of s, now in closed loop, was, as we found in the last thing, was g of s over 1 plus f times g of s. And so if we arrange this using this definition, we have g naught plus 1 plus s over omega p over 1 plus f times g naught over 1 plus s over omega p. Hopefully everyone can see that one. And now we're going to multiply the top and the bottom by 1 plus s over omega p to get that this is equal to g naught 1 plus s over omega p plus f times g naught. And we had previously defined f times g naught as this value t, which is the DC loop gain. And so what we see is that this is going to be 1 plus t plus s over omega p. And if we arrange this in a form that's more similar to what we had started with, so we want a standard form where this leading term here is a 1. We get we can factor out 1 plus t over here. So we'll get 1 plus s omega p 1 plus t over g naught. And so now we can make kind of qualitative determinations about the DC gain of the closed loop system as well as the bandwidth of the system. So what we see in this case is that the DC gain is now g naught over 1 plus t, and the bandwidth is now, so this is the minus 3 dB bandwidth, is now going to be omega p times 1 plus t. Any questions about that?
How'd you turn S over WP into T?
Where did I do that?
Can you go up to the?
I just rearranged.
So right there, you can see it. You go G naught over 1 plus S over WP plus F over. Oh, wait.
So this F times G naught becomes the T over here, if that's what you're asking about. And the S just moves to the end.
Oh,
and then
okay.
I factored out by 1 plus T.
Oh, okay. Fair enough.
Mm-hmm. Okay, so we can now think about. So what we see here is that in closed loop, we reduce the gain, but expand the bandwidth. And so, this is actually a really useful property, because it turns out when you're making an amplifier, you have to deal with some really, really slow poles. So as we saw in class earlier, when you do open circuit time constant analysis, if you have a huge resistance and some insignificant capacitance, that can give you a pretty large pull. And real amplifiers are generated with, or created with the same techniques that we are beginning to see in class here. So it's kind of expected that in some cases an amplifier will not have such a high omega p as we see there. And you would have seen this in the lab if we had gotten to do that in person. But omega p won't be so large, or won't be so large, but G naught might be large. And so this technique, by putting it in feedback, allows us to possibly extend the bandwidth just via the feedback while cutting our gain. And that kind of makes sense, because it seems like, if we have like a gain that's on the order of a couple thousand, we can't really use that in most applications, just because our output is limited by the output swing, which is directly constrained by the VDD or VSS of our amplifier. So if we don't want the output to rail, then we are going to need to use some feedback, and this gives us the added benefit of extending the bandwidth, which can improve the settling time. The amplifier will be faster in that sense. So if we wanted to find the unity gain frequency here, we can note that that'll happen when the gain, so let's see. So if we extended the bandwidth to the point that the DC gain was 1, then the unity gain frequency, you'll be able to note that the gain will be 1 up until a point. So the situation that I'm kind of referencing is that, so this is 0 dB, which is gain of 1. So if we put it in feedback such that this was the case, then this frequency, this new omega p that would result from the feedback, would be equivalent to the unity gain frequency of the system to begin with. So I think the professor would have gone through this in lecture. But effectively, this omega p naught, when this is the case, will be the unity gain frequency of the amplifier to begin with, which will just be the DC gain times the initial bandwidth that we started with. And this is the gain bandwidth product that is approximately constant. I believe it's an approximation just because of there's like a factor of 1 or something in the in-depth derivation. But this is a tool you can use to quickly approximate the not only the unity gain frequency of an amplifier, but also just by dividing by a factor here or there based on the feedback factor, you can also find the effective bandwidth in different closed loop scenarios. So any questions about what I did so far?
Yeah, I guess I messaged the question in the chat, but that factor of 1 where it's like approximately equal is just for inverting amplifiers, right? Or yeah, I think there was no factor of 1 with non-inverting.
Which factor of 1?
That you were talking about where it's like approximately equal.
I haven't done that derivation in depth. It might be the case. Maybe come to office hours and ask about that one. This is kind of just like a very broad rule, and it generally holds regardless of the configuration, as long as you have some sort of feature. So what is S?
Okay.
Yes, yeah. So S is like the Laplace S, like maybe if you're talking about this S means like j omega, at least for stable Fourier systems. And then, yeah, so we answered Rami's question about the factor of 1. Okay, so I think if hopefully that kind of reinforces something that you saw in lecture already. But I think if we have done that, then we can take a look at at a small example. Let's see. So Mark had brought up finding input and output resistance in feedback and how that differs. So let's see. So we have covered the idea of feedback, and so I guess we'll get into so let's first cover non-idealities of real op amps. So the first one is finite input and output resistance. So if we start with our initial model, okay, so I'll actually just list them out. So the first one is finite input and output resistance. And so for MOS amplifiers, generally Rin remains around infinity. So this is not such a big concern for most of the op amps you're going to use that are MOS. But for BJT amplifiers, as we've seen, there's that R pi, which can cause finite input resistance. So in that case, you can see sometimes with a BJT op amp that it's actually drawing current from the input terminals, which is not something you typically see with MOS amplifiers. And just because it's easier, typically we like to assume that the input resistance is high. So this is not really the most critical thing to care about for MOS amplifiers, that is. But for BJT amplifiers, if you ever do use them, you kind of have to account for that. And output resistance really depends on the topology. So you can't use any rules about MOS or BJT for that one. It kind of depends on what's going on inside of the op amp. Although, as we covered in Piazza, I think from a great question, output resistance really depends on what type of amplifier you want. And op amps are typically voltage to voltage amplifiers. So what does that mean we want our out to be? We want it to be low or high?
You want it to be low.
And why is that?
Because you want the majority of the voltage drop to be on the load itself, not in the op amp.
Yeah, so there's going to be a voltage divider. So we include, so this is the open loop gain of the amplifier, which was like that G naught that we looked at before. We have that times some V plus minus V minus. Then we have our R out. And we have some R load here. And this is a voltage divider. So we want R out to be as low as possible, such that R load has as much of the voltage dropped across it as possible. So hopefully that makes that clear. Right. So that is the issue of finite input and output resistance. And let's see. So we can think about finding the feedback factor of a circuit that has such non-idealities. So I was going to draw one for you. This is R1, this is R2, and this is the out. So if I said that this one had finite R out, we can find the feedback factor in this case. So how about we give that a shot? So what I want you to do here, and then the other consideration is that it has finite R out and it has finite open loop gain. So this isn't actually something that I mentioned as a non-ideality. So maybe I should put that as a zeroth non-ideality. So finite open loop gain. That was kind of covered implicitly in the kind of first few steps, just because we assume, or actually kind of the second step, we assume that the G of S has some G naught with a one pole settling behavior. And so the G naught is our finite open loop gain because it's impractical to make that infinite. So in this example here, we have a finite R out, as I covered before, and then we have a finite open loop gain. So that means that in our op-amp model here, where we have V plus and V minus, the open loop gain here is some finite number. I'd like you to find the output resistance of the circuit which is different from the output resistance of the amplifier. I've actually just given that to you. That's R out. And then also find the feedback factor, F, and loop gain. So I'm going to put you into, so I'll give you a few seconds to write that down. But I'm going to put you into breakout rooms, and hopefully you can hash that out and then come back in a few minutes and walk me through what you did. So let us.
Wait, so what does it say? Output resistance of the circuit.
Yeah. So hopefully that worked. Let's see. Yeah, it looks good. So let's open the room. So scram, get to work, and then back and tell me what you did.
This meeting is being recorded.
Yes, welcome. Okay, breakout room 2 is still hard at work, but I guess you have to other stuff, so we'll close that.
Wait, did you already solve it?
Well, I hadn't actually solved this one beforehand. Looks like it's kind of tough. So I did some of the steps, but you can tell me how to do the rest, I guess. Yeah, I guess, yeah, that's definitely solvable. It's tractable. So yeah, I probably won't just solve it out, but I think giving you the foundation should be good enough. I think 2 might actually be easier than 1. So that was a bit of a silly question for me to ask first, but we'll see how it goes, or how you understand it, that is. Man, they're going right to the wire. They've all been expelled from the room. Okay, well, I hope you were in deep discussion. So does anyone want to kind of tell me how they approach the, well, I don't want to do 1 first because 1 is kind of tough, but let's do number 2. So did anyone get around to finding the feedback factor in the loop gain of this circuit?
Yeah, feedback factor is R1 over R2 plus R1.
What? So the feedback factor is just going to be, F is going to be the ratio. So if we have V minus here, V minus over the V out. So in this case, V out is at the top of this VCVS here. V minus over V out is going to be the feedback factor. So
Right, isn't that just equal to R1 over R1 plus R2 times V out? I mean, well, you divide by V out, so it just becomes the voltage.
So let's draw this one out. So we have V out, then we have R out, then we have R2, we have R1, and this is V minus. So you want to tell me
I see what
again
you're saying.
what the answer is?
So then it's over R1 plus R2 plus R out.
Yeah. So yeah, I think the wording of the homework question that looks kind of like this, if not exactly the same, is finding the feedback factor from V out, but really we mean the output inside of the amplifier as opposed to the output outside the amplifier, because the outside amplifier output is not particularly useful if we have some R out that is finite inside of the amplifier, right? That'll attenuate it further. So hopefully that makes sense. You know, with the feedback, we can easily find the loop gain. So loop gain is just going to be A open loop times F. So I think you can do that trivial multiplication. I don't feel so scared about calling that trivial because it's literally just this times A open loop. Okay, so with that out of the way, does anyone know how to find the output resistance of this? And it's actually probably more difficult than I thought it was, but maybe you can surprise me.
Isn't it just R out in parallel with R1 plus R2?
In feedback?
Oh, and feedback.
I didn't disconnect the feedback for this one.
Ooh, interesting. You made it harder. Oh wait, I know. Yeah, this is wrong.
Did you just leave the breakout room because you thought it was easy? Okay, what about the other room that was deep in discussion or something?
Hey, Nilesh.
Yeah,
Josh.
what's up?
How'd you guys' room do it?
We're thinking. Oh, go ahead.
No, go ahead. It's okay.
Basically,
We're thinking-
we're still
I
discussing.
didn't really have anything I was gonna say.
Josh, what do you think?
I mean, we kind of have to draw it out, and in this case, we can't ignore the dependent voltage source. because V in goes to 0 because we null that independent source,
Right.
but V minus still has a voltage.
Right,
So we need to
exactly.
use that. And it basically becomes like a voltage divider, or like a parallel circuit of like R out and the current source, as well as the two feedback resistors going to
Yeah,
ground.
so essentially there's like, you have to account for, so this is what we tack on at the end over there. And we want to find the ratio of VT over IT. That's how we do R out in general. And so we'll see that the finite gain comes into play here because we have this multiplication happening, and V minus just comes about from the simple voltage division from here to here. And then you can, from this expression, you can write the actual V out here, right here. And then you can do some sort of nodal analysis that looks something like this, and then you'll eventually be able to find VT over IT. And it'll look kind of ugly, maybe. But that's kind of the point, to show that feedback changes things. So yeah, that's the subject of the homework. So hopefully that gives you an idea of what the homework's going to look like if you haven't started yet. So yeah, with that out of the way, we can cover some more non-idealities. So let's take a look. So other non-idealities include, let's see, current, I think it's now number 2. Voltage and current offsets. So how we model these is that we take our non-ideal op amp, and then we decompose it into non-ideal parts, which are these current offsets, current and voltage offsets in this case, and an ideal op amp at the end. So this is ideal now, which is great. And we have our offset VOS here, as well as additional currents that look kind of like that. So this would be I minus, and that would be I plus, right? And so typically how we specify these is that VOS will be some value, and then we'll give usually something like I plus minus I minus will be some other value. And the reason why we give this like this is that so these input currents will kind of come about more frequently, simply just because the actual it kind of depends on the circuit technology. And so the reason they're given as a difference is that it kind of depends, like which terminal takes in more current kind of depends on which configuration the amplifier is put into. So typically how I'll analyze this is that, so when we're kind of judging which circuit is better from an offset perspective, we want to first judge like how different the output referred offset is. And so to do that, we find V out as a function of VOS, and we find V out as a function of I plus minus I minus, noting that we can kind of do this via linear superposition. So zeroing out the sources that we don't want to analyze at any given point. And then we can add at the end. And an additional point is that for the purposes of analysis, if we can tell that one current or the other might be easier to analyze, or so an example of this would be if we had something like an inverting configuration. We have something like this, and we note that there are current offsets. It is actually easier to say that all of the current goes through this source, because that will give you your worst case output offset, as opposed to current going through this source and going to ground in the case of infinite input impedance. So our worst case offset is going to come when the current goes through this source, and then in that case you can find the effective output voltage as a function of this current just by virtue of the current going over a resistor or something like that. So the second trick is that I was going to write here is that you can choose to put more of I plus minus I minus in one of I plus or I minus, just to find the kind of worst case. So yeah, that's covered in the homework, and I think you can probably do that. In any case, we have 5 minutes left, so I have to do the last few. And the last concept, I think, is going to be slew rate, if I'm not mistaken. So slew rate is like a very, very nonlinear phenomenon. It occurs when the core limitation in our circuit is that we have, so if we have, so the reason this occurs is that amplifiers have maximum source or sink currents. And so how this arises is that we have our amplifier here, and then there's usually some output capacitance here. And so an expression we can find is that the change in voltage, so in this case would be output voltage, change in output voltage as a function of time is actually directly equal to this output current over the load capacitor. And that actually just comes from the kind of capacitor dynamics. So like if we start with the equation Q equals CV and then we differentiate both sides, we get dQ dt is equal to C times dV dt, and dQ dt is nothing except the current. So that's kind of like a fundamental limitation of capacitors. And this arises in our circuits because the amplifiers can, as we design them, can only give a maximum amount of current based on the topologies and the transistors that we use. So this places a limit on the maximum slope of our output characteristic. So the slew rate limited case is when initially we are just spending a lot of time charging up capacitor. So the output voltage as a function of time is very linear. And then at some point, which is not really the focus of this class, but at some point we'll resort back to what is called band limited response. This is a bandwidth limited response. So we can kind of, so the assumption that I'm making for this response here is that the amplifier transfer characteristic is something like we saw before. So it's something like that. And so if we take a look at what the transfer, or like what the step response would be. So this is a step response, by the way. If we take a look at what the step response would be in the case of a bandwidth limited response, then we'll note that that actually looks something like this the whole way through. It's very rounded as opposed to this straight line here. This is the SR, slew rate. So in this case, this was the slew rate. In this case here, via math tricks, we'll note that this change in voltage as a function of time is actually just equal to the omega of the pole times the input voltage. So if we want to check whether a output response will be slew rate limited or bandwidth limited, we can just check to see if which one of these is minimum. So if the SR is less than omega p times VI here, then what's going to happen is that it's actually going to be slew rate limited just because this slope is less than this slope. But if the opposite is the case, then it's going to be, the response is going to look like this. So yeah, that's more or less what I wanted to cover with slew rate. If we have any conceptual questions, please ask now. Otherwise, I did have like a really good example for this that I wanted to go through. So you're welcome to stay for that if you want to. Otherwise, I think this is more or less the conceptual basis. So any last questions, please ask them now.
I have a question on the difference between current bias and current offset. Is one to like prevent the other or something like that?
So a current bias, so we don't typically provide external biases for our amplifiers other than VDD and VSS, which are voltage biases. Typically, based on that, the amplifier can determine its voltage levels that it needs to operate. Current bias is typically internal to the amplifier itself as determined by like VDD and VSS and other circuitry like that. So the concept of current bias is not something that you will need to worry about with these non-ideal op amps, which are abstracted away from the design of the amplifier within the kind of triangle there. The current offsets are actually, they arise from mismatches in the device characteristics within the amplifier. And so the effect is that at the input, it seems like the amplifier is drawing current or something like that, just because of how it's laid out. But that's not the same as a bias necessary for the operation of the circuit. So, you know, the current bias is actually just the amplifier drawing current at steady state when it's operating, when it's being biased internally. And so that's something we have to account for when we're using it, but it's not something that we need for it to necessarily work, kind of like that.
Okay, that makes more sense. And I think Rami asked something in the chat
Sure, let me take
related to that.
BJT base current. Yeah, actually, yeah, that's true. So BJTs do need an input current in order to work. And so that won't be the same as the current offset, just because the current offset arises from the mismatching of the devices, whereas the current bias is necessary for it to work. So what'll happen is that in our models, the current offsets will arise even in our small signal models for the amplifier, whereas the current bias is not something that shows up in the small signal model. It's just a DC thing. Hopefully that makes sense.
Yeah,
Okay.
thanks.
Okay. So really quick, if for people that stick around, I want to do a quick example that kind of shows this step response thing. So let's take a look. I have it. So if we say that we have an amplifier that has a finite gain and nothing else, that's non-ideal about it. And we analyze it in closed loop and open loop. I'm going to draw this closed loop configuration. And the open loop configuration is going to look mostly the same, except the negative terminal is going to be grounded. So really quickly, can anyone, oh my God, not fitting, but can anyone tell me what the loop gain or what the feedback factor of this circuit is?
One, right?
Yeah, it's not a trick question, it's just one. This is a unity gain buffer after all. So yeah, so what we can expect from this is that because we showed that ACL is approximately equal to 1 over F, we expect the closed loop gain to be approximately equal to 1 as a result. So that's why we have this, we call it the unity gain. And then here we have an open loop configuration, which is just like a standard thing. So if we're going to analyze this in the Laplace domain, so Laplace domain involves usage of these S's. We can say in this case that V out. Actually, let's first analyze the open loop case. So in this case, we have V out is equal to just the gain, which is given over here, times V in, and the minus terminal is grounded, so we don't really worry about that. So if we take V in to be 1 over S, which is a voltage step that looks like this, with a magnitude of 1. That's in this is in time, the time domain, and this is the Laplace domain. Then we see that our output Laplace transform, which is a function of S, just to remind you, and I guess I wrote out. So that becomes this. And so one useful trick is that the inverse Laplace transform of 1 over S times 1 plus S over omega p is equal to 1 minus e to the negative omega p times t. And so this is what we call the single pole settling, because we have this is one pole and a step, and we see that the step eventual final value is 1, and so that's this 1 here, and then we have the settling of the pole where an exponential is gradually reaching this level of 1 as we go through time with this time constant 1 over omega p. And so in this case, we get that in time, V out as a function of time is going to be a open loop times 1 minus e to the negative omega p times t, just by linearity, because the Laplace transform is linear, so we can carry this a open loop through this. And so what we see here is that, I kind of mentioned this before, but a open loop is super high, and so output will probably rail before we see this. And additionally, omega p is really slow, and so this will settle slowly as well, which kind of is not good on either count. However, if we take a look at the closed loop response, we can see that it performs better in a lot of ways. So here we have a open loop with that function times v in minus v out. And if we rearrange terms, we'll eventually get that v out times 1 plus s over omega p plus a open loop is equal to a open loop times v in. And then we end up with v out is equal to a open loop over 1 plus s over omega p plus a open loop times v in. And if we factor out some stuff, we see that this is going to end up with something like this times 1 over 1 plus s over omega p times 1 plus a open loop times b. And so in this form, we see that we have some gain error due to finite gain. And we also see an extended bandwidth due to loop gain. The loop gain here is just a open loop and feedback. And so if we use similar tricks to put this back into the time domain, we'll see that V out as a function of time is now going to be a open loop over 1 plus a open loop times 1 minus e to the negative omega p times 1 plus a open loop times t. And so in this case, we see that we have a smaller gain, which is about 1, which is achievable if the input voltage as a function of time is within VSS and VDD. And so that's usually a reasonable assumption to make. And then we also see that this time constant is going to be, this bandwidth is extended. So this will settle much faster. And that's really how this closed loop, feedback has saved our response, because in the first case we had a really slow settling and an unachievable gain, and now we have an achievable gain with much faster settling, especially if a open loop is high. So yeah, that's basically it for this example. I just wanted to show you how to find the step response from the given configurations, and so you can use that as a resource later, and I'll definitely post these after discussion. So unless we have other questions, I think you're free to go.
Thank you.